Hello everyone. In this video we're going to talk about theory and simulation of free vibrations for a cantilevered beam, or beams in general, but here we're going to focus on the boundary condition of a cantilevered beam. So here is a cantilevered beam with length L, which is fixed at x of 0, and here is an infinitesimal element of the beam with length dx, and the external load on it is shown by px dx in general upward, where px is the intensity of the load per length, and you have the shear force on the left, the shear force plus increment on the right, the moment, bending moment on the left, the bending moment on the right plus increment. And here, if we look at equilibrium in the y direction, the forces you have are P dx and V plus dV, where basically in the upward direction, V and Px dx are added, and then V and negative dV are subtracted. So these two V's would cancel, and so this dV downward should be equal to Px dx upward, and that is your first equation. Then you take some of the moments about this corner of this element, and if you do so, then if you go with counterclockwise positive, you have m plus dm positive negative m, so that m and that m would cancel, and this force V is passing through that, so it's not going to do anything. And so the other things that create moment about that corner, in addition to m and m plus dm with respect to this corner, is this V plus dV, right? Or I assume in here, the way it's written, it's taken with respect to this side, with respect to the right corner, although it doesn't make any difference. But here it's taken with respect to this right corner, so you can see that, and it's positive, counterclockwise positive, so you have this one positive, that one negative, then V dx also negative, and then the centroid for the force, or the center of action for force Px, is in the center if you assume it's uniform. So it's going to be Px dx, which is the equivalent force times the distance, and in this case the distance is half of the x, so it's going to be Px times the x squared over 2. And if you set them equal and cancel the m's, then you'll get your second equation here. And what we'll do, this term is, it has a higher order infinitesimal compared to those. So if these terms are, like, for instance, 10 to the negative 3, this guy is 10 to the negative 6. So we neglect this in comparison to the other terms. So the two equations you'll get is dv over dx is p, and then dm over dx is v. Okay, and these are two well-known equations that you know in the formulas for Euler beam. Okay, so if you combine them, then you see that the second derivative of m with respect to x is going to be px. Okay, so from both of these you'll get this result. Also, you know, in a beam, the bending moment is related to the deflection y by m equals ei times second derivative of y with respect to x, where I is the moment of second moment of area for the cross section of the beam, and E is the Young modulus. So if you combine these two now, you'll get what? You'll get EI, the fourth derivative of y with respect to x, equals px. Okay, and this is what you had as the Euler beam. Okay, this is the well-known equation from which, if you knew this load density, you could find the deflection of the beam in static condition for all sorts of different loadings. Okay, so this is what we used in solid mechanics. Now in vibrations, nothing is static, the stuff are moving, so we need to replace this function p of x, and here, since it's free vibration, the only force really is the inertial force. Okay, not gravity, because again, this y here is measured from what? So if we have to add it here, this y is measured from static equilibrium. Okay, so we say deflection y is measured from static equilibrium, and also, and it is assumed to be small. Okay, so going back, as I said, this force Px is due to inertial force, and by inertia we mean force equals mass times acceleration. So this kind of force we are talking about. Or in other words, you say sum of the forces equals mass times acceleration, right? And here, remember, P is not the force, it's force per length. Okay, is force per length. Now, if this is my force, okay, if I divide it per length, what do I get? Well, A is second derivative of y with respect to time, which you can see. Mass per length, here we assume that the cross section of the beam as well as the moment of area, second moment, and Young modulus are constant along the beam. If they are not, then here this relation is not going to be just like that. Okay, this relation that you can see is not going to be like that. It is going to be second derivative with respect to x of e of x, I of x, times second derivative of y with respect to x equals p of x. Okay, so if e or I are not constants, then you have to bring them inside the second derivative and then take two derivatives. Most of the time E is, unless the beam is not from homogeneous material, but I can change. If the cross section is not uniform, I can change. But in this case, we assume it is for simplicity, and we assume I is constant. So that's what we have. And now the question is, what is m over L, where m is rho, the mass density, times volume V. And volume, you know, it's equal to cross-section A times length. So if you divide length by length, this term here is going to be what? It's going to be rho times A times acceleration. And that's what you can see here. Rho times A times acceleration. The only external other thing we have is negative sign. Why negative sign? Because here you know from dynamics that the inertial forces are basically in the negative of the applied force. Okay, so one way to write Newton equation is write F equal ma. Okay, the other way to write it is you consider this to be inertial force, bring it to the left side and write it like this. And then call this guy the inertial force, and as you can see, it's in the negative of the direction of applied forces. So in this case, where P is up, then ma has to be downward, and that's why you get that extra negative. So if you plug that in, now I have my governing what equation for the vibration of the beam, okay, the 1D beam. And here I divide both sides by EA, so you will get rho A over EI, divide by EI, not EA, divide by EI, so on the right side I get rho A over EI, and I call it a parameter called beta to the 4. And so your equation becomes fourth derivative of y with respect to x equals negative beta to the 4, second derivative of y with respect to t. And this is what? This is the vibration equation of a 1D beam, okay, with all the assumptions that we mentioned. Now, how can we solve it? This is clearly a partial differential equation. And again, like the wave equation in the string, it's just a product of the terms. There is no addition or subtraction, so still I'm going to use the separation of variables method. So I assume that y is a separate function of x times a separate function of time multiplied together, plug 2 back into 1, and then I'll get this relation. And if I divide both sides by f times g, I get this relation, where here the left-hand side of the equation is all functions of x, the right-hand side is all functions of t. And as we saw for the spring, the only possible scenario is both sides are equal to a constant. And again, as we saw, the constant has to be a negative number. And we call that negative number negative omega n squared. Why? Because here my g function is a harmonic function. And so the second derivative of that is negative the frequency, natural frequency squared times g. And so my g function is a harmonic function as expected. And my f function, now the fourth derivative of that, minus beta to the 4 omega n squared times f equals 0. Now here I come up with another definition. And I call this beta to the 4 omega n squared. I just call it kn to the 4. Remember, beta is a constant number in our case. So since this guy depends on subscript n, I just call it k sub n to the 4. And if that's the case, then the fourth derivative of x equals to kn to the 4 times f. And that linear ODE is going to be a combination of harmonic functions and the cosine and sine hyperbolic. And you know, the hyperbolic functions are really exponential functions, okay? So it's a combination of exponentials and harmonics, okay? Because here you have to solve for the characteristic equation of s to the 4 minus 1 equals 0. And as you know, there are 4 roots. 2 of them are positive, negative 1, which are corresponding to the hyperbolic or the exponentials, and the 2 other ones are what? Plus and minus I, the complex number. And those correspond to what? These harmonic responses. Okay, so this is the solution for x, this is the solution for time, and there are 6 coefficients to be found. So how do we find them? Well, this is a fourth order in terms of x, so we need 4 boundary conditions. 4 boundary conditions. What are they? Well, it's a cantilevered beam, so at this end here that is fixed to the wall, y has to be 0 as well as y prime, the slope. At the cantilever, at the fixed end, the y, the deflection, and the slope, they both have to be 0. But on the free end, on this end, m, the moment, has to be 0, as well as the shear force v. And m, as you know, is related to what? Related to second derivative of y. So that means y double prime has to be 0, because that constant ei cannot. And v, remember, v is d of m over dx. If you plug this m up here, v becomes what? We will become ei and then y third derivative. And so when v is 0, that means the third derivative of y has to be 0 at the free end. And these are exactly what we have down here. And if you plug them in, you'll find that constant c is negative of a, constant d is negative of b. These are for y and y prime at location 0 at any time is 0. And then at location L, m, which corresponds to y double prime, is 0, or f double prime is 0, and the third derivative of y, or f, equals 0. If you get that, then you get these 2 equations, 8 and 9. Okay, now you have to solve 8 and 9 for what? For the 2 unknowns a and b. Okay, you have to solve them for a and b. And by the way, c and d have already been replaced back into 4. So before we even go for 8 and 9, we plug this c and d back into 4, right? So they go into 4, and then we apply the 2 next boundary conditions on 4, and we get equations 8 and 9. And if you look at 8 and 9, there are 2 equations and 2 unknowns, a and b. And the thing is, this is a homogeneous set of equations. And these terms are not 0, so you cannot find both a and b from here. And if you find a from one and dissolve it in the other one or eliminate, you'll get this equation, okay? So what I have here is basically you took one of these terms to the other side, so it becomes like a times this parenthesis equals negative b times that one. Then take this term, this b to the other side, it becomes negative b equals this. And now we divided both sides of the equations together. Now, of course, we swap this equation, the two sides of it, and then we divided. And if you divide, a and a would go away, negative b and negative b would go away. So we get the ratio of these terms all equal. And what does this give you? Well, here we have to now cross multiply. If we cross multiply and simplify, and keeping in mind that cosine hyperbolic squared minus sine hyperbolic squared equals 1, and then cosine squared plus sine squared also equals what? 1. If we use these two equalities, this new equation will be reduced down to equation 10, which is cosine hyperbolic of KNL cosine of KNL equals 1. Now, what are we solving here in 10 for? We are solving for what? We are solving for this Kn times L. This is our unknown. Why is it our unknown? Because Kn involves what? It involves the frequency omega n, which is also another one of our unknowns. So it's not just A, B, C, D that are unknown. This natural frequency, we need to find a formula for it. So this equation 10 is going to be that formula. What's the problem with 10? The problem is this equation cannot be solved analytically. It has infinitely many solutions, and you can only solve it numerically, okay? So if you solve equation 10 numerically, as I said, it has infinitely many solutions corresponding to infinitely many natural frequencies. And here I have provided you with the first three solutions. So if you solve, then you can find that K1 times L squared, which is also equal to beta squared omega 1 L squared, equals, if you solve, one of the roots is at 352, the other one is at 22, the next one is at 61.7, and there are more and more solutions. But the good thing is, from these guys, you can find the relation for the first three frequencies, natural frequencies. Omega 1 is 3.52 over beta squared L squared, omega 2 is 22 over the same thing, omega 3 is 61.7 over the same thing. Where you see omegas, they do depend on what? They do depend on L. So of course, the longer the beam, the smaller the frequency, also beta. And remember, beta 4 was what? It was rho A over EI. So let's see if these frequency formulas do make sense. So clearly you see that if L goes up, the natural frequency goes down, and it's expected. It's a longer beam. It takes it more time to oscillate, so omega should go down. What else? If A or rho, any of them goes up, that means beta goes up. If beta goes up, omega 1 goes down. Is that true? Yes. If you have a beam that has a bigger cross-section or from a denser material, of course it is harder to oscillate it fast, so the natural frequency is lower. On the other hand, if E goes up or I goes up, beta goes down. If beta goes down, omega goes up. Would that make sense? Yes. A stiffer material is going to oscillate faster. And if you have distributed the mass further away from this neutral axis, also you can make the system rotate faster. Now there is one relation, an extra relation from 8 and 9 that we can find. And remember, from 8 and 9 we eliminated A and B. We found this important equation 10, which gives us, if we solve it numerically, the natural frequencies. Also, what you can do, from either of them, you can find a relation directly between A and B, and that is this equation what? Equation 11. So it's not from 8 and 9, it's basically from 8 or 9, okay? So let me do it as this. From either one of these, you can find a relation between A and B, so you find B as a function of A, Now that you have b as a function of a, c as a function of a, and d as a function of b, and since b is a function of a, that means you found out b, c, and d all as a function of a. So if you plug in 6, 7, and 11 all back into equation 4, now the only unknown in f of x will be this a. Everything else is known. And so if you do so, this is going to be the solution for f function. And this a is a constant that we'll talk about it, but the rest of it is clearly what? Your mode shape. So the mode shapes of the beam are this kind of function. And they are not a simple function like we had for a string. It was a simple sine function. It's more than that. Here you have cosine hyperbolic, you have cosine function, you have this whole constant number, and then you have sine hyperbolic and sine of x. So you have all 4 functions in the mode shape. So mode shapes are more complicated. And if you look here, 3 of the mode shapes are drawn for you. This is for the first mode shape. It looks kind of like you apply the force at the end, right? The second mode shape, you see this beginning part of it is kind of not bent too much, and then it goes down, and then goes up, and then goes down. So you get 1 node here. And then the third mode shape, it's going to go like that, and here you get 2 modes. As I said, as the number of mode shapes goes up, you get 1 more node as you go up on n, 1 at a time. Okay, so these are some of the mode shapes that you can see, and the location of the nodes are shown for you. If you are curious where these nodes are, it is showing it for you as a function of L. And so basically that's where this function is equal to 0. So again, you have to solve for a crazy big nonlinear equation to find those numbers, but you can do that. So now I have 1a that I couldn't find, and in a g I have 2 unknowns, h and p. So when I multiply f to g to get y, a is going to be multiplied by both h and p, and I'm going to give them some name. So a times h, I call it r, a times p, I call it s. If that's the case, then you get your complete solution here in equation 13. So it's going to be a summation, n goes from 1 to infinity, y again summation from 1 to infinity, because you have infinitely many mode shapes and infinitely many frequencies. Where this part here is the g function, and this part here is the f function, and it has 2 unknowns, r and s, to be found. And how would you find them? Well, this PDE is also second order in terms of time. So that needs also 2 time conditions, 2 initial conditions. So here we need 2 initial conditions. And here, again, for simplicity, let's assume that this is beam. You see, that's the problem. When you copy from your previous material, you always have a chance of missing something. So if we release the beam from rest, which means y dot at all points at time 0 is 0, right, this guy. If you do that and take a time derivative, you'll get this equation. That huge thing in brace is the f, and this omega n Rn is coming from this term, which becomes a cosine. Plug 0, that becomes 1, so r stays. This becomes a negative sign. At 0, that goes away. And if this is 0 for any x, that means this Rn has to be 0, which you can see in 15. And then y at x of 0, the initial displacement of the beam. Here, we choose an arbitrary function for it, q of x. Now, again, you have to pay attention. This q of x must what? Yes, it must satisfy the boundary conditions. So you define a function between 0 and L as long as it satisfies these what? These 4 boundary conditions. On the left end, y and y prime are 0. On the right end, y double prime and y third derivative are 0. Okay? And if you have such a function, you can consider it to be your initial displacement function. And if you do, then from there you can find this Sn. Again, if you look at it, it's just like a Fourier series. So all you need is to multiply that huge of a thing by basically q of x integrated from 0 to L multiplied by 2 over L. And once you find Sn and Rn, that means you have the entire perfect solution. Okay, so this is analytical exact solution for it. Now, if we want to simulate this system with finite difference and go about it numerically, remember this was the governing equation with beta being that. So here we have to discretize these derivatives. For the fourth derivative, I use this what we call 5-point operator, central 5-point operator, which uses the y of 2 nodes to the left of it, the y of the node itself, 2 nodes to the right of it, over dx to the 4. And for second y derivative, we use the same thing that we used in previous video, a 3-point operator central, which uses the previous time point, the current time, and the next time point. Okay, and if we plug it in, remember the goal is to find this guy, the next time point at the current location in terms of everything else. If you do so, you'll get this important equation, which is your update equation. So in this update equation, you can find the next value of the node, the next deflection at the next time point, if you know the current value at the node, if you know the current value at the next 2 nodes on the right and the next 2 nodes on the left, and what the previous value, the previous time value of the node. So this is your update equation. Now we need to apply the boundary conditions as well as the initial conditions. So what were those? The first one was at time of 0, y equals q of x. And then y dot at time 0, here we assume it's 0. Remember, we assume the system is starting from rest. So y dot at time 0 is 0. For y dot, we use the same derivative, forward derivative that we used last time in the string. If this is 0, that means, and this is at time 0. So this is your t equals 0. If you plug it in, that means the y at the second time point is the same as y at the first time point. The initial y's are equal to the y's at the next time point, and these are all equal to q of x. So these are your initial conditions here. Now let's apply the boundary conditions, right? Remember, there are 4 of them. One is y at location 0 at any time point is 0. That's 1. The other one is slope at location 0 at any time is 0. Again, for a slope for first y derivative, I use the forward x derivative formula. And again, if this is 0, that means the y at the second node, the first node on the left, they all don't move, but also the second nodes, the second elements, right? On the left side, they also will have no displacement. Because if they do, then you will have a non-zero slope. So you have to also kind of fix the this deflection of the second node on the left, otherwise you will have a non-zero slope. Now at the right end, at x of equal L, y double prime and the third derivative are equal to 0. And for y double prime, you see again, here I'm using a 3-point approximation, but this is not a central one, this is a backward one. Why backward? Because if you are at the very right node at L, there is no extra node on your right side. So you have to only calculate the from L, you have to go back to the left. So here we go to 1 node to the left of L and 2 nodes to the left of L and set that equal to 0. That means this numerator equals 0. And then for the third derivative, again, we use a 4-point operator. And here we use not only the L, the node before L, the 2 nodes before L, and 3 nodes before L. Third node before L. And here, I assume this is x cubed. Let's make sure I don't have a mistake in my notes. That is 0. Again, that means the numerator is 0. And if that's the case, then I'll get 2 equations. One is equation 16. The other one is equation 17. And if you look at these two equations, 16 and 17, what are the unknowns here? What are the unknowns? Well, the unknowns are the deflection at L and the deflection at L minus dx, the node before L. These two nodes, I cannot use the update formula for them. Why not? Why can't I not use the update equation for node at L and the node before that? Because in order to do that, I need two nodes to the right-hand side. And I don't have two nodes to the right-hand side of these two. So for these two, I have to determine them from boundary conditions. So here, I solved 16 and 17 for these two unknowns that I just showed you, right? This was one, two equations and two unknowns. I solve for them, and I'll get this important equation 18, if you might want to call it 18. So these equations 18 will give you y at L and t based on the 2 and 3 nodes before it, and y at L minus dx and t as a function of, again, 2 and 3 nodes before L. Okay, so let me bring it on this side. You see? So I can call them 18 and 19 maybe. So I use these two to update the values of these deflections of the node at L and the node before L. And for the first node and the second node, what should I use? I use these two conditions, that their display deflections are 0. So the first two nodes, that they have nothing on their left side, and the last two nodes, that they have nothing on the right side, I use these equations, okay? I use these equations, and you know, let me give some good numbers here. If you don't mind, let me add some numbers. So I call this guy 16, right? Let's go ahead and do that. So that is 16. And here I need these equations 17 and 18, right? Which are at the boundary condition, and then this guy is going to be 19, this guy is going to be 20 and 21. There we go. And finally, the question is, can I pick the value of dt and dx any way I want? No. For stability, we need some stability criterion, and this is just like previous video. We use the same condition that we used last time. In this case, the thing that needs to be less than square root of a1 over a2 is the square of this term that is in the update equation. So we need to look at this term here. Let me draw something around it. So we need to focus on this one, this guy. The square root of that is what we compare against the square root of a1 over a2, okay? And the square root of that is dt over beta squared dx squared. Okay? Remember last time? Let me go back. Remember last time the term that we compared against it for the string was what? Again, it was the square root. Let's go back, take a look. There we go. You see, it was this term. We had this, and here we used the square root of that, c dt over dx. So here we use the same thing. The coefficient that we have in the update equation, we look at the square root of that and compare it against the square root of a1 over a2. But this time a1 and a2 are not both 4. I mean, a1 is 4 because I'm using the same, but for the x derivative, it is not 4, and I just fixed this. It's the fourth derivative of x, not second derivative of x. Again, that's the problem of copying from your previous videos. So for the fourth derivative, if we go and look at the operator that we have, you'll see that some of the absolute value of the weights that we have in the finite difference approximation, in this case, a 2 is not equal to 4. If you see, I have a 1, I have a 4, I have a 6, a 4, and a 1. And if you add those numbers together, you're looking at 16. Okay, so the number for A2 is what? 16. So if you plug 4 and 16 here, that's going to be 1/4. The square root of 1/4 is 1/2. So that dt over beta squared dx squared has to be less than 1/2. Last time it was 1. This time it's 1/2. Because we use a higher order operator with a lot more terms and with bigger maximum sum of absolute value for the fourth derivative of x. And so here I wrote my MATLAB code for you. And I made the beam 1/2 meter. And I used a bunch of elements along it. As you can see, it's like 21 elements. And here I need to use a very small time step size. Otherwise, you will not get that parameter less than 1/2. So I only simulate for 2 seconds. You can go more. You have to wait more. And so you see here I'm using literally 4 microseconds. Okay. And even with that, if I calculate my parameter here, this guy, which I called it alpha, that parameter was, for me, it was 0.6467, a little bit less than 0.5. Okay, so I had to go that much down for the time step to make the system stable. But I did that, and here you see again, I started all of my solutions at 0 pre-allocated. The first 2 points on the left, the first 2 nodes at all time, they are 0 to have 0 deflection and 0 slope. And then also you have the these are also, these two are also boundary conditions. Let me add that for you here. These two also boundary conditions. These two that you see in the update loop, these are those boundary conditions that I have here in 20 and 21, which they have to be constantly updated. They are not fixed like the first 2 nodes that are just 0, right? It's not like that. Okay, like 17 and 18. The last 2 nodes, you have to always find the 3 and 2 nodes from L, and based on those, you have to update based on 20 and 21. So you see, I put those in the update equations. This is my big update equation, which works for all the interior nodes to third node from the left all the way to third node from the right. And for initial condition here, you can see that I forced the second time point and the first time point to be the same, but for first time point, I used this cubic function here. And why did I choose this cubic function? Because it satisfies all of the boundary conditions. This is actually the deflection of a cantilevered beam under the external force P at the end. And I chose it such that the deflection at the end, which is PL cubed over 3I, it's basically about 10 centimeters or 0.1 meters. So I chose the equivalent force that I need such that for initially, I have so much force that brings this beam down to 10 centimeters, and then, or positive 10 or negative 10, doesn't matter here. Of course, the way I define it, I assume it's going to be positive. And then here, the initial conditions applied. And the beam here is made of aluminum. So this rho and this E are from aluminum. And I use the cross section to be not a square, really, it's rectangle, with a rectangular cross section, which is 5 centimeters height, 20 centimeters width. So maybe I have to say W equal that, and then let's put it there. Then H equals 5 centimeters. That helps you when I calculated this I with basically BH cubed over 12. That's the cross section, and A is just W times H. And so everything is calculated, and at the end I have what? I have the simulation, and I'm not going to show it for all time points. I'm going to jump every 200 time points. I'm going to jump, so it doesn't take forever. And let's take a look at the beam. Here we go. If you want, you can, instead of 200 points, you can skip every 100 points, or you can use some pause to slow it down. But this is what? This is the cantilevered beam with 21 elements and a ton of time points between 0 to 2 seconds. Okay, and you see even with jumping every 200 points and only 2 seconds, you see it takes quite a bit of time because you have a ton of what? A ton of time points, right? You have a ton of time points in this Y solution. As you can see, it has 500,000, right? Let's see. Yeah, 500,001 time points and 21 nodes. Okay, so hopefully this video was useful to you. I'll put a download link for this animation for you under the video description. Hopefully it teaches you something useful, and feel free to download it and learn something more by changing the boundary conditions or initial conditions. Thank you so much for your attention. I'll see you in the next video.